Yeah, and just as a quick reminder for people who don't know, this presentation is part of SOMAS's spring seminar series here at Stony Brook, Southampton. So there's one a month, and there's going to be one more. Kevin Reed is a professor of atmospheric sciences who'll be giving a seminar the first Wednesday of May. His presentation is going to be on climate change and how it affects coastal storms. And he's an excellent speaker, so I highly recommend you come and attend that one. But meanwhile, here we are. We get to see everybody who's attending. This is quite a display we have here as people zoom in. But again, very excited to be here live and excited for the people who are online. And you can see the subtitle for this presentation is the Watershed of Destiny, and you'll find out why. We'll leave that as a surprise for now. I want to dedicate this presentation to Nancy Kelly. Maybe many people don't know Nancy Kelly, but she was director of the Long Island chapter of the Nature Conservancy. And before that, she was the president of the group of the South Fork. So really a great environmental champion who did a lot of incredible work for many decades. And unfortunately, she's no longer with us this year. So I'd like to dedicate this presentation to her and all the wonderful work she's done on behalf of the environment, really, like I said, literally through the decades. And I'd also, of course, like to acknowledge the Gobler Laboratory students and staff. For those of you who are here in person, you got to see the posters they put together, and you'll get to look at those again afterwards. And they really are both the boots on the ground and the fins in the water that make all of this happen. And without them, well, I really would not have much to say. So I'm eternally grateful for their ongoing dedication to protecting our coastal waters. And well, we live streamed the poster session, and so you can keep up with us on social media via Instagram, Facebook, and Twitter as well. And so I'm going to start out with that concept of a watershed. And I'll come back to it again, but we all know the situation we're in here on Long Island. Anywhere you are on Long Island, no matter where you are, you're in a watershed. And all activities on land affect the water that ends up under our ground and under our feet in the ground. And that water couldn't be more important. That's the water we drink and the water we don't extract and drink discharges to our surface waters and can have very important consequences there as well. So really, it's the center of everything that goes on in Long Island when it comes to, like I said, drinking water and surface waters. And we know that the situation on Long Island has been changing over time and how that's affecting both the quality of our groundwater on many fronts. And that's been with population rise. You can see we've had, depending on how you want to do the calculations, I'll just say a significant rise in the amount of nitrate in our aquifer. And again, that's what discharges the surface waters. It's the water we drink. And I've shown this slide before, but I think for me, it's very impactful. If you look at the y-axis, this is the total population almost of the United States. And so essentially it's showing that 200 million people in the United States their drinking water supply is less than 1 milligram per liter of nitrate. Right? And you can see on average where the groundwater is for Suffolk County. And there's a lot of diversity there as well, but you just take the average, and first of all, we're way at the tail end, right? There's only a few % of people with groundwater concentrations that high. In the last, and very importantly, the EPA has a groundwater standard of 10 milligrams per liter to prevent something called blue baby syndrome. Now, on the one hand, we would say, okay, great. At 10, we're way below that. But what I've been tracking over time, and now some of the medical doctors and epidemiologists at Stony Brook University Medical School, Renaissance Medical School, have been tracking, has been the epidemiological literature that keeps growing with regards to the medical effects of nitrate at concentrations below 10 milligrams per liter. And you can see I have a series of scientific papers here that I'm citing, and you can see many that have come out, or several in the last just several years. And they're showing, at least at an epidemiological level, that much lower levels of nitrate have been associated with elevated levels of cancer. And the mechanism here is pretty clear. It's via creating something called nitrosamines. And so there's a lot of diversity in the amount of nitrate in groundwater. it's really hard to see all these, the x-axis here, but maybe that's for the best for right now. This is 87 different zip codes across Suffolk County. And this is now actually the tap water, right? The water that's getting delivered to homes. And so on the one hand, you can see there are many, many communities where the levels are very, very low. And in fact, in that range of less than 1 milligrams per liter. But what you can also see, there are other communities where the concentrations on average are significantly higher. And sometimes higher than that average, and many that are above that epidemiological threshold. And again, that at least been called out with regards to epidemiological studies. Now, we've actually been collaborating with some of the epidemiologists at the medical school to look at the rates of different types of cancers in Long Island. So I'll just point out here that there's, for example, higher rates of bladder cancer in Suffolk County compared to New York and the United States. And that's one of the cancers that are promoted at just 2 milligrams per liter and higher with higher nitrate. Now, this is epidemiological evidence. This is data from the New York Department of Health showing that there are regions in Suffolk County that have higher than average levels of kidney cancer. Again, which is something that's been associated with, as I show here, epidemiological evidence of high nitrate in groundwater. And importantly, that area with high kidney cancer is not an area with lung cancer. So if they overlap, we'd say, oh, well, these are just smokers. But that's not the case here. It's not smoking, it's something else potentially in the environment. And don't get me wrong, I am not saying that nitrate is the cause here, but I'm saying that there is reason to be looking more carefully at all this. And obviously, good motivation to have nitrogen levels in our groundwater and drinking water as low as possible. Okay, but the levels are rising, and beyond the effects potentially on our drinking water, we also know that there are effects, of course, on marine life. Now, the studies are in. There's been more than 7 different studies done in the last decade. They've all come to the same conclusion that primary source of nitrogen in groundwater is from wastewater in Suffolk County, and also on the north shore of Nassau County as well. So we now know that also, and not the south shore, because the south shore is sewer. And we also know that that has consequences, of course, for our coastal zone. So this is from the Nature Conservancy. Both of these images are, but of course this one's even more fun to look at because it gives you shows you the connectedness of what's going on in the groundwater to what could be going on in surface waters. And of course, every year the Gobler Lab puts out this map, which is just literally at this point, it's a 4-month snapshot. What did we observe in the summer of 2021? So part of State of the Bays 2022 is sort of retrospective. And so here you can see just between the months of June and September of 2021, all of the different marine and freshwater harmful algal blooms that we documented, as well as all the different dead zones that is oxygen below the DEC standard of 3 milligrams per liter. And that was documented by our lab, but also by Connecticut Department of Environmental Protection. And so what you can see, and I should also say when we declare a harmful algal bloom, for example, for blue-green algae bloom, it's based on standards set forth by the DEC. So what you can see is these events are widespread. They're on every coastline. They're quite common here on the South Fork, but throughout the South Shore, the North Shore, and everywhere else. And if you look at this pattern and you look at something called the Suffolk County Subwatersheds Plan that came out in 2020, you can see that not only is nitrogen levels rising in our groundwater, it's also happening in surface waters. So this is data from the Subwatersheds Plan that shows a 50% increase in nitrogen on the North Shore, similar amount out on the East End, and a similar amount on the South Shore. And on the front of those harmful algal blooms, which I'll of course go into detail on, we have several that are toxic to humans and also several that we know are actually harmful to marine life. And I'm just going to go through a few of these now. We'll start with our inland waters, our lakes and ponds. This is Lake Agawam in Southampton. And you can see the contrast of that water compared to the blue ocean water. And that's a cyanobacterial, also known as blue-green algae bloom. We worry about these because they make toxins, the most common of which is microcystin. When that was first discovered in the 20th century, the first name for it was fast death factor because of the way it can elicit mortality, at least in laboratory animals and experiments. Also has been shown to have carcinogenic effects. Also has been shown to take down animals as large as elephants. So this is a news story. This is from 2020 from the plains of Botswana. a mystery of over 300 elephants, some of the largest mammals on the planet, dying from consuming blue-green algae. And while this was a news story, I can say that the scientific papers affirming this have come out since then. Beyond elephants, we also know that pets are at risk to blue-green algae blooms. This is a CDC study that's shown that there's been hundreds of cases of dog poisonings over the years. And we've had those events here in Long Island and specifically here on the South Fork. And that's why the DEC tracks these events very carefully. Once a week, we actually work with them on this effort. And in doing that, they're discovering year after year, there's more water bodies across New York State with these events. But if you look all across New York State and you look at all of the counties, again, this is a little bit hard to see perhaps, but if you look carefully, what this essentially is showing is that no county has more blue-green algae blooms than Suffolk County. And that's not for lack of looking. What I want to emphasize is we're looking at 53 out of the total 62 counties in New York. So it's not like, oh, we're just looking harder in Suffolk County. No, it's actually that they're looking all over the state, and that Suffolk County comes in with almost 50% more than the closest county, which is Putnam County. And we know there's a link to nitrogen here. I've written papers about this. And the thing I want to point out is that toxin microcystin, if you look at that toxin, that's a nitrogen-rich molecule. It's almost, some people hypothesize, a nitrogen storage molecule. Essentially, it works. If you give this organism, microcystis, more nitrogen, it makes more of this toxin. And it works in reverse as well. So getting down the nitrogen levels can also make these organisms less toxic, which of course is what's most important. Again, just looking at some retrospective, last year was a pretty bad year for rust tide. It started early in August and was pretty persistent all the way through into October. And these are just some aerial shots that are taken by Chris Paparo here at Stony Brook for Shinnecock Bay. Tim Corwin on his glider with aerial shots there, really with Peconic estuary from north to south shore. So very, very widespread. And I'll come back to rust tide later, but we know this is what we call an ichthyotoxic harmful algal bloom. It can kill fish. We have experienced that firsthand at the Marine Lab here. We also last year saw a mahogany tide in the spring in many places across the South Shore. And I'm highlighting that here specifically. Maybe I'll admit John. I'm highlighting that specifically because in the last year, I stumbled across a report that was put together specifically by Cameron Engineering. The report was from 11 years ago, where they talked about specifically these mahogany blooms and specifically saying that, well, they're not toxic to human and they're not yet a problem in Long Island waters. Well, that's changed, and just in the past few years, because we're now seeing this every single year. And then beyond mahogany tides, we need to point out a study that I can start calling out people in the lab. Craig Young is here and has done a lot of work on this particular harmful algal bloom that is new to Long Island, but is persistent and is now really worth talking about. And so when you see water like this and you go down to the seaside, you don't need a scientist to tell you that something's amiss. And so this is Daisy Siphona japonica. It's actually a seaweed, and you can see what it does to the water. These are scenes from Great South Bay from 2019, and it's, well, not water you'd want to swim in, and it's actually a seaweed. And it occurs almost every year. These are images that I got as late as last October, again in Great South Bay. And I'll highlight it more, but you can see the algae is on the shoreline dying and then releasing this red pigment. Now, this doesn't look good, but it also has some human health implications. There's been studies that have shown very, very clearly that when you have these seaweeds and they get in the state of decay like that, they can potentially release toxic gases known as hydrogen sulfides. When those get into the atmosphere, there's all sorts of, and I won't go through the medical conditions here, but this is a journal article in The Lancet, which is the second most impactful medical journal on the planet, that described more than 10,000 people going to the emergency room just in one small tropical country being exposed to seaweeds washing up ashore. So on this particular front, I guess I'm going to try to hide this for us all here live. There we go. Daisy Siphona japonica, you can see that the species name japonica, it comes from Japan. So it's indigenous to the Pacific. It invaded Europe during the end of the 20th century. And it's really just been in the last 15 years or less that it's been present here in North America. And when we look at what's happening here, the work by Craig Young is pointed out, and we published this paper just last year. This seaweed is all over the south shore of Long Island, Great South Bay, Merchants Bay, Shinnecock Bay, and even into the Peconic Estuary. And the question might be why? Why is it suddenly showing up on Long Island? Well, in that paper we published last year, we did some simple experiments and examined what's the growth rate of the seaweed if you grow it under normal conditions, if you give it more nitrogen, more carbon dioxide, or you give it both of those stimulus. And what you end up seeing is that there's an effect from nitrogen, an effect from carbon dioxide, and an additive effect of both of these things. So it likes the conditions that we now have specifically here on Long Island, and that is higher levels of nitrogen and seasonally elevated levels of carbon dioxide. We looked at the seaweed tissue and used something called nitrogen isotope tracing to get a very simple answer as to where the nitrogen is coming from. When you do this, you can really distinguish two sources of nitrogen, fertilizer or wastewater. You get a negative value, -3, if the seaweed's assimilating just fertilizer-based nitrogen, and you get a +10 value if it's just wastewater. And so what you can see is with all the values here, this is Craig's survey all across the South Shore, between 75 and 100% of nitrogen being assimilated is from wastewater. So this is, we have many ways of telling us that it's wastewater, and in politics, they say it's the economy stupid. Well, maybe we say it's wastewater stupid on the nitrogen front. The seaweed and its isotopes don't lie, so to speak. Okay. And so the question is, why would we worry about this outside of human health? Are there any effects potentially to marine life? And the answer is yes. And again, we go to Craig Young in a paper that actually we hope to have published soon. This is in revision right now. But essentially, you can see this is the exposure to fish to the decayed seaweed. And I should really probably emphasize that. So what you're looking at here is not the seaweed in its ideal state. So when you look at, for example, down here, there's the seaweed, it's dying off here. And so we think that happens seasonally because it gets too warm for the seaweed, right? And that's a problem because we don't expect it to get cooler with time. We expect it to get warmer. So there may be more of these die-off events. So we've studied specifically, is the live seaweed a problem? How about the decaying seaweed? And so what this shows is, firstly, the fish don't mind the live seaweed whatsoever. They swim in and amongst it, and that's great. But when you have a die-off event and you see the bay is turning red, that's a problem because you can see here, you're having the die-off of two different species of fish. In one case, we didn't provide aeration and those fish died really, really, really fast. But even when, in another case, we provided aeration and made sure the levels of ammonium, which can be toxic, were very, very low. Even in that case, the fish, you can see we lost half of the fish in just 2 days and almost none survived 1 week. So there's something going on within this decayed seaweed. We did the same experiment with hard clam larvae and we got the same result. You can see here about a halving of the survival rate when you expose it to the decayed seaweed. Does fine when the seaweed's living. So, and then the last thing we've done in the last year is trying to figure out what is in that decayed seaweed. Why would this be happening? And to that, we partnered with people from the Center for Clean Water Technology, and specifically our, you can see here, our tandem mass spec, specifically to identify what are the compounds. And in doing that scan, what we identified is a specific compound that's highly enriched in the decayed seaweed called clerpin. And so what you can see here, I'm not an expert on this, but this is the M/Z is the mass to charge ratio, right? So it's picking out the specific compound, and there's a peak at that mass to charge ratio, and that's whether we're decaying the seaweed on our own in the lab, or whether we're getting just the naturally decayed seaweed that came right out of the field. So you're seeing the same exact peak, and that compound clerpin is found in other seaweeds and has been shown to be toxic to both fish and shellfish. So we think this is one of the reasons that this is a harmful algal bloom on Long Island. And so now we can look at the history of harmful algal blooms on Long Island. Now we can really look at it. And you know, there is a long history. It goes back to the mid-50s. In the 1950s, Merchants Bay did not have an inlet. And so you had a lot of duck farms and a lot of waste coming from those duck farms, and very intense what were known as green tide blooms that actually were harmful to oysters back in the mid-50s. The Ash Wednesday storm of 1954 created the Murch's Inlet and started flushing out that bay. And through that decade, the duck farm started going away and those blooms ended. And we entered an era on Long Island where we had the most robust hard clam fishery in the history of New York, but also at the time, the most robust and productive one in the United States, and also the most productive bay scallop fishery in the history of New York as well. And that went on for a nice stretch of 25 years. The brown tide came in 1985 and put an end to the scallops for the first time, at least. And then we've had a succession of other harmful algal blooms show up with time, and we can now add the mahogany tide, which again, reports of it not being present. We now know it happens every year, and we know Daisy siphonia was not present and not even on the continent 15 years ago, and is now an annual issue, at least on the South Shore. And we know there's a link to nitrogen, but I'd like to get a little even deeper in that. And so for that, I made this table pulling out these 8 different harmful algal blooms and then going into the literature. Is there a relationship with nitrogen? And what you can see here is that there is lots of evidence and lots of publications, both globally, but also done right here for the specific examples, making the link between high levels of nitrogen and the occurrence of these harmful algal blooms. I think it's important if we're going to make conclusions and make links, they need to be supported by science. And, that's what I'm showing here in the table. Okay. Another outcome to be concerned with regards to high nitrogen and algal blooms is how that might affect oxygen levels. Because as we have algal blooms and they may decay, that can lead to the consumption of oxygen and the reduction of oxygen levels in the water column. And the DEC takes oxygen very seriously. There's not many water quality parameters that the DEC has standards for. Oxygen is one that they do have a standard for. And essentially what they want to see is ideally levels above 4.8 milligrams per liter and never less than 3 milligrams per liter. So, one thing that's interesting about looking at oxygen is the fact that the levels change between day and night in any given water body. And that's because we know there's photosynthesis by day, and that at night, there is no photosynthesis and oxygen levels go down. And so here's just an older data set, but one that I think is really useful because it was a collaboration with a gentleman named Rick Winfield from the EPA, where we were sharing data. This is actually also somewhat collaborative with the USGS, but sharing the data and looking at the patterns. And if you look at this pattern of this oxygen, on the one hand, it's a mess, right? What are the oxygen concentrations? But this is what the data really looks like when you measure it carefully. And the reason is, you can see every day there are peaks during the day and valleys at night. And so what I want to point out here is that if you're really looking at the minimum oxygen level, that's what it is for this whole month. But if you happen to be going out and making the measurement at other times, so for example, at 7 in the morning or at 8 in the morning or 9 in the morning, you're going to get a very, very different answer. Right? But if you look at the standard, that standard is not linked to time of day. It just says shall not be less than 3 milligrams per liter. And so, if you want to understand if you're hitting the target when it comes to oxygen, if you're going out if you looked at that data set and you did your monitoring at 11 o'clock, and just think about okay, you've got a job, what's your job to do? Measure oxygen, you wake up, you go in your equipment, you go out to the water, you make a measurement, and finally, maybe it's 11 o'clock. That data set would tell you, okay, even if you're going out every single day, you're that diligent, but you don't get there till 11 o'clock, you'd say, yep, most of the time, everything is good. But depending on when you get out there, you get a different answer. And if you had a continuous monitoring device, this is where we've been using, you find out that actually it's not meeting that standard 97% of the time. Another data set similar to this that came to light in the last year was work done by my graduate student, Chris Wozni, where he used this device here, put it into the sediment, assured that it was above the sediment by having a platform that it went on, and then measured how oxygen changes with depth with time. And saw the same wiggles, but also saw that if you're making measurements, and this is, I believe, Bellport Bay, and these are measurements up on a dock that's floating, going up and down, and you can see the oxygen goes up and down, but it doesn't look too bad, right? It's making the standard. But here's what happens when you get lower and lower. And the bottom line is, in some cases, the lower you get, well, not in all cases, the lower you get, the lower the oxygen is, right? And so on the one hand, that's just interesting, right? Low, and makes sense because we know sediment is a big demand for oxygen. But on the other hand, you know, what are the marine organisms we're managing oxygen for? And if it's bivalves that live on the sea surface, well, then that could be an issue. And then the other thing I'll just mention is that, again, sort of a recent revelation is the fact that not only this is a very messy looking plot, but I think a beautiful one. It's showing over time, so a 24-hour cycle from midnight to midnight. Here's noon. The levels of oxygen and pH. I believe this is in a spot in the Peconic estuary, and it's showing both dissolved oxygen, but also that's colorized, but also pH. So here you see that day-night wiggle, but now it's many, many days right on top of each other, right? And so it looks messy, but you get the point, I hope. And that is, at night, those pH and oxygen levels are very, very low, and they're high during the day. And Stephen Tomasetti is here and published a paper in the last year showing that this really matters. And I just wanted to highlight this, that in this particular experiment, he was raising blue claw crabs and specifically looking at how do they do under perfect conditions, if the oxygen and pH is sort of at a moderate level or a very, very low level, or if it's going back and forth between that low level and a perfect amount, which is what we're seeing in the environment. And what he's seeing is that people might have thought, oh, well, at least it's good during the day, they're probably okay. For these blue crab larvae, that's not the case. And in fact, you can see they do just as bad as if it was at that very low level constantly. So they're not getting a reprieve. Okay, so this leads us into climate change that we've talked about before, and being in the Anthropocene, and the idea that we're now in an era where humans are overwhelming the environment and controlling climate change. And we know that last year temperatures reached, we're not an all-time record. You can't quite see what they were. There we go. But the last, I believe, 6 or 7 years are the highest ever on record since measurements began. And we know that temperature is just one of multiple stressors that are happening in coastal zones. And I've been known to call this all 4 of these things: warming, acidification, hypoxia, and harmful algal blooms, the 4 horsemen of the ocean climate change apocalypse, because they're all happening together. You know, I'm sort of zipping through this a little bit here. I want to make sure I'm not going on for hours, but we know that high CO2 leads to acidification. The high CO2 via the greenhouse effect leads to the thermal stress, and warmer oceans hold less oxygen. And we know there's more harmful algal blooms. So there are your 4 horsemen. And we know these all come into play and can affect things like bay scallops. And we know the scallops have collapsed in the last several years. And so I'm proud now to highlight again some of Stephen Tomasetti's work that he's done looking into this and how might this be related to some of these climate change stressors. Now, you've already heard me talk about rust tides, and I told you last year was not a great year for rust tide. Last year was not either. This is an ichthyotoxic algae. Its bloom season keeps increasing. This is a paper we published a few years ago. The redder you see on the map is the more days per year the bloom season is expanding for Cochleardidium. And so essentially what this map shows, you can very clearly see, we're in the bullseye for the expansion of this season, to the point that, and this data set goes to 1982, in the 20th century, our waters weren't warm enough for this organism to hit its maximal growth rate. Now we have a 2-month window for the rust tide, and it's taking advantage of that window. There's also a role for nitrogen. This is a paper published about a decade ago, but showing that this organism grows faster when you give it more nitrogen and does so more frequently than other types of algae. And it's, in addition to being ichthyotoxic, it's also lethal to scallops. So this is one of the first papers we published on this particular rust tide organism. Very simple experiment using water from the Peconic estuary and also exposing scallops to that, as well as filtered seawater. And you can see the scallops do not like being around the rust tide. So Stephen's shown that temperatures are changing, and these are the trends since 2003 through 2020. And you can see here the overall temperature change over that period is in some cases as much as a degree Celsius. And on one hand, it's easy to say, oh, just a degree. Well, okay, that's not so bad. But the thing to recognize is that that's just in 17 years, right? Globally, in some scenarios, maybe it only goes up 2 degrees for the rest of the century. Bottom line is, and we have other data that goes back before this, the bottom line is that we're warming much faster here in Long Island, particularly during summer, than the rest of the globe is on average. And that's important, looking at things within a season. And so, for example, our springs aren't warmer, and maybe on some days this week and last week, we wish they were, but they're not any warmer statistically, but our summers are. And that's problematic because already at that point, marine organisms are at their maximal tolerance. So they're hitting their maximal temperatures. They're hitting temperatures that, they had not seen in the past. In other seasons, the season can shift. So a spring organism, that's having warming, well, it'll just maybe, it'll occur earlier in the year. But when you're at your maximum, and that hasn't been seen in the past, that has more severe and serious implications. By a law of physics, the warmer it gets, the less oxygen's in the water. And so we can't change that either. And again, this is probably even more severe if you're a benthic organism on the bottom, where we know the oxygen levels are much lower than in the surface waters. So, Stephen, I don't know if this is on your poster or not, but you can talk to Stephen afterwards to hear more about this. But he did a very simple experiment looking at temperatures that we're seeing in the Peconic estuary and also looking at oxygen conditions, and essentially found that, well, if you just put up the temperatures, the scallops do okay. If you give them moderate temperatures and the oxygen is lower, they'll do okay. But if you give them both of these things together, they don't do okay. And the survival is, well, you can see here, only lasting not even 3 days. He also did a field experiment replicating those same conditions, or I should say actually those conditions also seen in the field, same temperature max, same oxygen levels, and again, no survival of the scallops. So certainly temperature and oxygen is an issue for the bay scallops. And it's not even the end of the story, of course, because we know if you combine nitrogen and higher temperatures, you're going to get more rust tide, and that the temperature alone and the rust tide alone is a problem for the scallop, and the oxygen is as well. So this is the perfect storm of actually what a lot of scientists are focused on. It's called multiple stressors. We know it's happening, and this is really a perfect example of how it can push and change ecosystems and fisheries with all these things coinciding together. And yeah, so these are the things to talk about there. We also do know that there is a parasite present in the scallops, although it's also present in places where the scallop seems to survive. So that role is yet to be fully sussed out. We also know that the food levels in the Peconic estuary, what the scallops are eating, have not changed. There was a hypothesis that the scallops weren't getting enough food because there wasn't enough nitrogen. We can cross that one off the list at least. Just overturning every stone. And if temperature is becoming a problem for the scallops, that wouldn't be the first time. Just as a reminder, we lost the Long Island Sound and Long Island lobster fishery. Actually, at the time, one of the most robust fisheries on Long Island. It just got too hot, and the lobsters have now moved to Maine. And actually, interestingly, it's now getting too hot in Maine, and the lobsters are moving to Canada. So, climate change is real, temperature change is real, and it has implications for fisheries. And I would encourage you to talk to Stephen afterwards if you want to discuss scallops further. Okay, so Watershed of Destiny. So we're back to the watershed here. And so I have actually, when I'm using this term, I have 2 meanings here. And the first one is, boiling it down, is that we're all in this together. And so I'm going to use this quote from Martin Luther King, where he said, in a real sense, all life is interrelated. All men are caught up in an inescapable network of mutuality, tied in a single garment of destiny. And whatever affects one directly affects all indirectly. And this is the interrelated structure of reality. And so that's one thing to recognize in a watershed. Like, it's, you can do all you want, but if your neighbors are not taking care of things and we're not doing it all together, that's not going to move the needle, right? And where we go from here is fully dependent on how we're all pulling in the same direction or not. And then there's a philosopher, Wendell Berry, who said, do unto those downstream as you would have those upstream do unto you. right? And that's kind of funny, but it also has some sort of irony as well, because you can think of that. Well, there's people who have these beautiful waterfront homes, right? But how the view they're going to get out of that waterfront home, what that water body looks like, is affected by the people, well, upstream of them, frankly, and how they're taking care of the watershed and the aquifer or not. And so the question is, what is going to be our destiny here on Long Island, right? For off the bat, like I said, we're all in this together, and it's either we go in one direction or the other. But just getting concrete about where things stand right now. This is from Suffolk County and their sub-watersheds plan, essentially showing a business as usual scenario, or the scenario where you implement the sub-watersheds plan and upgrade the over 200,000 septic systems by the year 2050. And you're looking at the levels of nitrate in the groundwater. Should have said that. That should be on the slide. Apologies. But recognize all the red, yellow, and orange in the upper left there, right? That's the level that is going to be a problem for ecosystems and maybe is a human health concern. And then look at how vanishingly, how much less of that there is in the lower right. So, that's, what's the destiny? And as Chris Clapp said before, choose your own adventure here, or choose your own destiny. And when it comes to our drinking water, it's a similar thing. Now, in some cases, you would hope the water looks like this, and this is an easy choice. But a lot of times that's not the case, right? All the water looks the same. But what's the water we want to drink? And I have some concentrations up here that are based on real world observations, right? The average nitrate concentration at Orient is now at over 100 observations at 10 milligrams per liter. Or the Bethpage plume, the highest level of 1,4-dioxane ever measured in groundwater in the United States. Or, unfortunately, right in my backyard, literally a half a mile from where I live, more than 1,000 parts per trillion of PFAS compounds. And thankfully, thanks to the town of Southampton, I'm on public water now. So not a concern. But these aren't made up numbers. These are real things happening today. And similarly, what kind of beaches do we want to have? You're looking at the right, the Peconic Estuary fish kill of 2015. Not the beach you want to stroll. What kind of bay do you want to swim in, right? And again, there's the Peconic. I believe they're both Great Peconic Bay, one with and without a rust tide. Here's, I believe this is Shinnecock Bay, with and without a brown tide. The choice is ours. Little excursion on controlling your short-term destiny. We'll be talking more about this in the coming year, but we actually, the Gobler Lab collaborated with scientists at Stony Brook University last summer to create the world's first water quality app. And we'll have, this will be an even more user-friendly release coming up Memorial Day this year. But this was used by a lot of people, even by students and in classrooms, with data, as you can see, on literally hundreds of beaches across Long Island, over 500,000 acres of shellfish beds, and all of the monitoring that this lab does as well. And so you can answer things like, how's the water? Well, if it's one of our water quality monitoring stations, you can get information with regards to what the most recent conditions were, levels of temperature, levels of oxygen. Again, we have the DEC's declaration of shellfish beds being open and closed. So, knowing where to dig for clams can be complicated in certain estuaries. So here's Eastern Great South Bay. This, of course, is a GPS-based app. So you'll have a little indication of where you are, and you'll know, am I in the open or enclosed area, or am I in the open area, or am I in the closed area? And so Baymen want to know, apparently, so, Alex. And same thing on beaches. So we had, you may recall, last August, we had some very intense tropical storms that actually led to a lot of beach closures. How do you know which beach you would want to go to? Well, this has data feeding into it from the Suffolk County Department of Health, Nassau County Department of Health, and the State Health Department. And indicating whether a beach is opened or under advisory. This is pulled down. This was an actual day last August where on the same peninsula on Oyster Bay, there are beaches that were open and ready and others that weren't. And you can click on each individual beach and get the record of fecal coliform bacteria, right? So you could literally then say, oh, well, I'm going to this beach, it's open now, but has this been cleaned? What does it look like? And you'll see some beaches are never going to have an issue with bacteria. Others may have them quite frequently. And you wouldn't know, but you will with this. So again, This app had a sort of a two-step installation last summer. This will be a standalone. We're just overcoming a couple of university policy issues, at which point it'll be on the App Store and the Apple Store. And free, of course, for everybody to use. It's just for your enjoyment and information. Okay, so as we choose our destiny and we think about choosing to mitigate nitrogen loads, we can look to Long Island Sound as a place where there's just been incredibly positive response out of the sound. Long Island Sound had probably the third largest dead zone in the United States every summer for the entire second half of the 20th century. Thankfully, the EPA came together and said, let's come up with a plan to fix that. And the Long Island Sound study said, we're going to reduce nitrogen loads by 58% to Long Island Sound. That began in the year 2000 and went very quickly because they were doing with sewage treatment plants. And so if you look at the hypoxic zones from the late 90s compared to after the changes were made, what you see are whole stretches of Long Island Sound that no longer, at least in this period of time, are experiencing hypoxia. And you can see compared to what that was like in the before. And here's the size of the hypoxic zone over time. And again, there's wiggle. Every time you get a super warm summer, as I mentioned, hot water holds less oxygen. It's more stratified. It lets less oxygen get to the bottom. So you do get some peaks and valleys. This is an ecosystem, but you can see what the trend is like. And beyond looking at that, this is a data set. I had to combine two data sets to make this, but this is the kind of correlation in an ecosystem. I have a bunch of graduate students here. They'd all be thrilled to get this correlation, right? And so imagine if your data sets look this good, but this is Long Island Sound. This is the nitrogen loading rates in Long Island Sound and the trend in the size of the hypoxic zone. And what you can see is how well correlated they are. The nitrogen levels drop, and on average, the levels of oxygen, the size of that dead zone is decreasing. So it works. So just turning to what can be done here and what is getting done on Long Island. I've mentioned the sub-watershed study many times. Suffolk County, by many people's declaration, was probably one of the worst counties in the country for wastewater disposal if you went back 7 years ago, with every single home taking that wastewater and directing it as far down into the ground and as close to our drinking water supply as possible, right? Not a good idea. But right now, you could argue that there's no county in the country with a better plan for handling wastewater than Suffolk County. Like I said, they're on track for upgrading 200,000 homes, and they've got a science-based plan to implement that, and the funding, very well funded, at least going through for the next 5 years or so. So I guess get while the getting's good. So there's the plan. You can see they're prioritizing very specific zones based on drinking water supplies and based on impacts on coastal waters. And again, taking these systems and upgrading them, they've got a series of on-site wastewater systems that have been approved and rate to less than 19 milligrams per liter. But at the university, I also direct the New York State Center for Clean Water Technology, where we're harnessing science to engineer clean water for the protection of public health, for the environment in New York and beyond. And we have a goal now called 0-10-2030, and we want to get contaminants in drinking water as close to zero as possible or undetectable. We want to get nitrogen coming out of wastewater systems below 10 milligrams per liter, systems that cost $20,000 or less, which is what the grant money is for right now, which would mean it be free, and systems that last at least 30 years. And our first exploration to this are our nitrogen removing biofilters, which are near passive systems that are based on just sand and sand mixed with wood chips, with a drain field overlaying both of these layers. This is showing the effluent from our systems in the red compared to some of the approved systems in the green and other systems that have not been approved. And you can see they're right amongst the best when it comes to nitrogen effluent. We do have 3 different versions of these. I'll talk about those momentarily. And beyond removing nitrogen, these systems are also taking out the other things we don't want in our groundwater, things like emerging contaminants. So for example, it's been able to reduce levels of 1,4-dioxane by more than 60%, which sounds, I don't know what it sounds like to you, but if you know the chemistry of 1,4-dioxane, it is very hard to get out of water. But these systems can remove 60% of that And you see here all sorts of other drugs and pharmaceuticals that are removed by somewhere between 50 and 100% by these systems. And that is better than sewage treatment plants and better than conventional systems. I'll just go back and say, this sand layer makes all the difference for removing these contaminants. No other system has that, and therefore they don't have the same level of contaminant removal. So we have 3 different iterations of these systems. We expect 2 of these systems to be provisionally approved by the end of the year, meaning anyone could install these. We have a 3rd system that we expect to be approved next year. Some of the technology out of those nitrogen removing biofilters, again, I mentioned wood chips. We've co-opted some of that technology to create something we call a wood chip box to operate with a regular advanced system. And that this could just go on to any system that already exists out there to improve its function. And we found these to be useful. So here's an example of a particular system that's been installed that was 2 systems in one location, one doing well and one not quite making the standard. We then installed the wood chip box into that system and got that level down significantly lower. So, you know, that's the important thing. And I'll just emphasize that, well, one, there's an opportunity to get these commercial systems even better. And that that you don't know what these systems are doing unless you're measuring. And so that monitoring these systems is very important. And I could say more about that, but I'll just leave it at that. And then there are other things that are going on to reduce nitrogen loads as well. And so I don't have time to talk about the Shinnecock Bay Restoration Program tonight. There's a poster out there. Tim Curtin is here and can tell you all about it, along with Michael Dole and others, Brooke Morrell. But you can see some of the highlights here. I'm going to just make these statements and I'll leave it at that, but they're eye-popping. Right? This program began in 2012. So since the program began, the landings of hard clams in Shinnecock Bay have increased by 1,700%. The densities of clams in eastern Shinnecock Bay have increased by 2,000%. You can see the data there, so that's where those numbers are. We haven't had a brown tide bloom in Shinnecock Bay in 6 years, and we're seeing the regrowth of seagrass. And I'll just say, with more clams, the bay is filtering at a much quicker rate. So this has been an incredible victory. And again, you can talk to scientists afterwards to learn more about you know, how this is coming about. Oh, and the last thing I'll just say with the landings of clams, the landings in the last year in Shinnecock Bay exceed Great South Bay. Great South Bay, of course, had the largest hard clam fishery in the history of New York, maybe in the history of the US, and is 10 times larger than Shinnecock Bay. So that says something, I think, as well. Last thing I want to pivot to here when it comes to mitigating nitrogen, and that is seaweeds. And you can see here seaweeds being autotrophic organisms, assimilate CO2, take up nitrogen, give off oxygen, and also give off what we call secondary metabolites. I'll talk more about that. But if you've been paying attention in the last, well, half hour plus, you know that we have problems with too much nitrogen, too much CO2, and not enough oxygen. So we have all the dials moving in the right direction with these seaweeds. One of the seaweeds we're working with a lot has been kelp, thanks to work by Mike Dole. In fact, I can say with all truthfulness that if it were not for Mike Dole, I'd have nothing to say today about kelp. He brought it to us with a collaboration with Greenwave. This is Brennan Smith from Greenwave, who came here in the first year Mike was here to talk about kelp. And before you knew it, we were growing kelp, and we've been doing great things with it on oyster farms. And so here's Brooke again. We established the first DEC permitted kelp hatchery in 2019. We've run it for the last 3 years. We're producing 50 to 100 kelp spools on our own, and also partnering with other groups and getting it out to other groups also. We got this technology first from Greenwave, and now we're passing on to other people like the Shinnecock kelp farmers, for example. And we've put kelp out on over 15 sites, which actually, as I look at this map, this really just shows the incredible hard work that Mike has put in during the last three seasons, everywhere from Fisher's Island all the way to the Bronx River estuary. 15 different sites. 10 of these are oyster farms, so co-growing these with oysters being grown out there, and that's important, and we'll talk about what that is momentarily. But just to give an example, here's the yields from a couple of years back, but you can see the yields are amazing. In just 1 foot of line, we're pushing towards 10 pounds of kelp. We're putting out lines sometimes that are 200 feet, right? So I'm saying 10 pounds in just 1 foot. So, and you can see the blades here. There's Mike having to get up on his ladder to show you a 12-foot kelp blade. And we don't have time to cover it tonight, but this was grown in 2 feet of water. And so again, crediting Mike, Mike was told by people on Long Island when he was going to grow kelp in the South Shore, they said, that is the stupidest thing we've ever heard of. You're never going to grow kelp on the South Shore. It's too shallow. You need deep water. You need 20 feet. I guess you don't need 20 feet. You can get 12 feet in 2 feet. In fact, our best sites have been on the shallow water locations. So you never know until you try. We've also found that these kelp take up a lot of nitrogen. There can be 3% nitrogen or more, and the amount of nitrogen they take up is proportional to the site that they're grown in, which means if you want to take out a line of nitrogen in a particular location, kelp's a good way to be doing that. And we've done some calculations of the amount of nitrogen being removed. If you had a 1 acre oyster farm, you could be removing up to 200 pounds of nitrogen. And well, that's as much as upgrading 8 to 18 homes with regards to their septic systems. Now, there are many caveats to that statement, and I'm not saying that it's one or the other, and I'm not saying that we're doing kelp instead for sure, because this, the septic system works for decades. You have to do this kelp every single year. But I'm just saying that this is certainly can be a tool in the toolbox. How does these aquaculture of kelp and other seaweeds affect the things we have problems with, like ocean acidification and like harmful algal blooms? Here's a more recent level of CO2, and you can see we've passed the 420 mark, and it just keeps going up. So again, how might we be affecting acidification and harmful algal blooms? Well, let's see how we can adjust CO2 or directly affect these harmful algae. So here's a study, again, Craig Young worked on a few years ago, not with kelp, but rather with specifically using ulva. And what we saw in this particular experiment, this is growing oysters. You grow the oysters with the ulva, their growth rate doesn't really change. You expose them to high CO2, that's ocean acidification. Oysters do not like that. You can see their growth rates plummet. But with the ulva, we could rescue those growth rates and improve them significantly. But how about kelp? It's a whole different species. It's a lot thicker blade. How might that affect ocean acidification? Well, we looked at this for some experiments as well. And we created in the lab, I'll first show a lab experiment where we created acidified conditions. For those of you, if you don't know, ocean pH should be about 8.1. So this is an artificial scenario where we purposely put in some CO2 to create acidification at a level we see in our coastal estuaries today. If we add in kelp, this is what it looks like. And so you can see in just a few days, the kelp shoot that pH way up. And this drop here is because Craig changed the water, and you can see just 3 days, you get not acidification, but basification. And it changes something we call the saturation state from being undersaturated, which is going to dissolve shellfish, to saturated, which is going to be perfect for shellfish. And so we also, this is a paper that actually is going to come out any day now, just accepted for publication, but similar outcome. Grow the oysters with kelp and no big change. Expose the oysters to high CO2 without kelp, and you cut their growth rates by 60 to 70%. Co-grow them with kelp, and you can fully rescue those growth rates. So here, again, this just to emphasize, in this particular condition, they're getting exposed to the same amount of CO2 that these individuals are. The only difference is the presence of the kelp. And of course, the big test was, can we do this in the field? One of the oyster farms that we get to work on a lot is Paul McCormick's Great Gun Oyster Farm, which is, he's been incredibly generous with the lab as far as allowing us to tinker and do experiments and explore. And so we did an experiment that Mike helped with, but also Craig Shion and Andrew Lumsden helped set up sensors. So essentially putting out oysters in 3 different locations, along the kelp lines, near the kelp lines, and then further away, and also having sensors out there to see what's happening to the chemistry. So if you look at the pH on this kelp farm, what you see is that, again, 8 is normal, and so we've got a little bit of a sag in the pH here. Not surprising, that happens in coastal zones. But when we looked at, this is the control site away from where the kelp was. When we look at where the kelp is, however, we see the levels of pH are significantly higher. It was strongest for the first several weeks. You see the day-night wiggle, but on average, higher pH. And when we grow the oysters, or when we grew the oysters and compared to away from the kelp, on the kelp, or next to the kelp, we see significantly faster growth rates for the oysters. So essentially showing that there is a benefit. It's not just a nice idea to grow kelp with oysters. There's an actual benefit to these oysters. They're growing faster. And of course, for an oyster farmer, that's important. It's going to get to market quicker, be able to make more money. We've also looked at other seaweeds. We love kelp here in the Gobler lab, but we also recognize that as temperatures continue to rise, the season for kelp is going to get shorter. So we need to consider seaweeds that grow during the summer. And one of them that we've been looking at is Gracilaria. It's a red seaweed. It's cultivatable. It's been grown all around the world. I've actually eaten it. It tastes good. A little soy sauce and sesame oil, sesame seeds. That was in China. But Colin Bennett is here for his master's thesis. Did experiments looking at how Gracilaria would affect the brown tide alga, which is also harmful to shellfish. So he grew it at 2 different levels of nutrients, 2 different levels of the seaweed, and the effects were very, very clear. Within just 48 hours, at levels of the seaweed that you expect to find in an oyster farm, you could essentially almost eradicate the brown tide. And this was just a laboratory experiment, but it just says that there's the potential for doing this, not just in the winter with kelp, but in the summer with other seaweeds to have benefits for the shellfish. Because again, if this is at an oyster farm, that brown tide can be very harmful to the oysters. And the cells were almost gone after 48 hours. And then just one other point on the kelp. The kelp coincides with time with regards to probably the most dangerous harmful algal bloom on Long Island, Alexandria. It makes saxitoxin. It's a neurotoxin. It's 1,000 times more potent than cyanide. And it causes paralytic shellfish poisoning. And we've had more than 7 locations in Long Island closed to shellfishing because of this. So we have Lane Sobers here, who published this paper. And you can see this is what an Alexandria cell should look like. And I call this the Alexandria cell spilling its guts. It does not like the kelp. And in only a few days of exposure, you see chlorosis of the cells and the dying off of these cells, at least microscopically. Lane also did experiments looking at the effects of nutrients on Alexandria. In this particular case, this is a 300-liter mesocosm experiment. This is the number of cells, no nutrients, with nutrients. And now here is nutrients grown with kelp. And what you see is you get a reduction in the amount of Alexandrium, in this case, by almost 4-fold. And then the final thing that Lane looked into was how does this affect the shellfish? In this case, not the growth of the shellfish, but the toxicity of the shellfish. So he very simply co-incubated the blue mussels with the Alexandrium and with the Alexandrium and the kelp. And what he found is when he co-grew the mussels with the kelp, he had significantly lower levels of saxitoxin accumulated into the mussels. And again, with benefits to the oyster farmers, if this got down even lower, there could be the difference between shellfish being marketable and not. So this leads to a concept I call the halo effect. And that is specifically that we're not going to solve harmful algal blooms and climate change with seaweeds. So let me just be really clear with that, right? That's probably an important statement. We're not going to solve our nitrogen problem with seaweeds, but we can have localized effects, right? And specifically on, for example, on oyster farms and other particular places. And I've shown you that we can suppress harmful algal blooms, reduce the toxicity, get that toxicity down below regulatory levels, increase the pH, increase the calcium carbonate saturation state, and rescue bivalves from ocean acidification. And with that, I'm done. So my conclusions is that excessive nitrogen loading from wastewater is an ongoing threat to coastal ecosystems, economies, pets, human health across Long Island. Climate change is accelerating and exacerbating these things as a multiple stressor. I've shown you that upgrading septic systems is a important tool for mitigating and reversing water quality impairment and removing other things we don't want in our drinking water supply. And that seaweeds hold the promise to mitigate water quality and impairment like HABs and acidification. And well, we didn't get a chance to talk about fertilizers today, but we may at another point in time. So I thank you all kindly for your attention. Okay, and so with this, we will attempt to have a both live and Zoom question and answer session. So let's see here. Maybe I'll start with this out with a question. Jim Arrowman asked, how does nitrate in groundwater become nitrosamine in drinking water? So that was about the human health effects. The nitrosamine doesn't happen in the drinking water, it happens in our stomachs. So when the acid from our stomachs reacts with the nitrogen, the nitrate in particular, it creates a compound known as nitrosamine. That compound is carcinogenic. It's the same reason you shouldn't eat a lot of bacon, right? Or hot dogs. There's a lot of nitrates in that and leads to the same thing. And we had the sound bomb, we'll go past that. Let's see. In regard to wood chip IA systems, do the chips have to be changed periodically? Do the chips accumulate any of the contaminants? So the wood chips, because the way the system is designed, the wood chips in particular, 2 of the 3 designs remain saturated. We believe that they are going to have a lifetime of decades. And I always tell the story, I once went to Denmark and went to a fjord. And there was a museum there. And in the museum was a Viking ship they had just raised from the bottom of the anoxic fjord. And it still looked like a Viking ship 1,000 years later. And with the upshot being that when you have wood that's saturated and anoxic, it doesn't degrade. And so it should last for quite some time. I don't even know what that means. Yeah, and in one of our designs called the wood chip box, thinking that you might want to be able to change the wood chips in the event, you literally can access the wood chips through a manhole cover and actually replace those wood chips. That is a possibility. Let me pause on those and see anybody in the room have questions. Yes.
Dr. Gobler, I think this is probably not true, but in the gardening world, if you plant a new plant in your garden that you think is going to be wonderful and solve the problem, but it's an invasive species for your environment, it takes over the garden and kills everything. I don't know anything about seaweed, but is that at all, is seaweed natural to the area? Like, is there an issue that could ever happen?
Yeah, so I'm just going to restate some of that, I think, for the people online. But the question is about invasive species, and invasive plants can take over a garden. Well, I think we've seen with Daisy siphona, Daisy, that red seaweed, that's an invasive seaweed, and it's taken over the South Shore. And one of the reasons that invasives can do so well, and I know, of course, more about the marine system, so I won't even speak to the garden, but in a marine system, one of the reasons the invasive species do so well is that they're new. And so there are things that eat seaweeds. And so our current ecosystems, we've got whether it's the fish or the snails or the birds, they know what they want to eat. They see something like Daisy siphona and they say, well, I don't know what that is, I'm not going to eat it. So they're eaten at a lower rate. And they clearly are releasing compounds that may be inhibiting other seaweeds also. So this, as an invasive, this has really acted like an invasive plant as well. Why don't I try another person in the room? I saw another hand. Yes, sir.
Yeah, is the nitrogen, when it's dissolved in water, does it form nitric acid? Does it contribute to ocean acidification in that way, in that regard?
So the question was about nitrogen in the water. Does it contribute to ocean acidification? No, usually nitrogen dissolved, whether in groundwater, it typically goes from ammonium to nitrate. In the ocean, in both of those forms, it doesn't have a strong effect on pH, thankfully. It doesn't turn to nitric oxide. So let's see if I'll try if I can see what I can. All right. Question, how do people know whether to eat seaweed that has been absorbing toxins such as Gracilaria? Okay, fair point. And so I'll just say that I was at an invited guest at a dinner in China when I was given the Gracilaria seaweed salad, and it felt like the most polite thing to do was just to eat it, which I did. But yeah, I think actually, but being more serious, I think the regulatory regime, the DEC, for example, is figuring out what do we do with seaweeds and what tests must be passed in order for seaweeds to be a food product. And that's being sussed out because there is interest, for example, in using kelp as a food product. Mike, I don't know if there's anything you want to add to that on the food front, but.
Just the kelp that we've tested for contaminants thus far
Oh.
on Long Island has come up very clean. So,
Good point, yes. So,
that's in terms of heavy metals and organic
yeah,
compounds.
so relaying what Mike said, we have tested the kelp, and it has at least the kelp that we've tested, both the Peconic estuary and the South Shore. All of the metal contents are within regulatory limits, no organic contaminants, and little to no bacterial contaminants as well. But that still needs to be sussed out, I think, at the regulatory level. Let's see. Question about how does this relate to freshwater ponds and how can we mitigate the impacts of nitrates using freshwater macrophytes? Well, that's an interesting, I actually was speaking to a group, believe it or not, from Illinois at a Zoom, gave a seminar earlier today, and they asked the same question. There can be competition between freshwater plants and freshwater blue-green algae. It's a little bit of a dicey situation, but I guess one thing I can speak to is in some lakes, when you eradicate things like invasive plants like Eurasian milfoil, you would want to do that, or lily pads even. That can be a good thing. You want to be able to move in your lake or pond, but that leaves potentially the water body, the water column open for microalgae to grow. So sometimes those aquatic plants can play an important role. Let's see here. I see KB has her hand up. KB, if you want to unmute and ask a question, if that's your intention, I would welcome that.
My question was answered. I was the one who asked about eating the Gracilarius. Sorry.
Okay, no problem.
I'll lower that hand.
Yep. Okay. Anybody in the room? Questions? Did I go back and forth? Yes, please. The first, Daisyophona, I think I want to say the first observations were certainly 2018, I think maybe even 2017, somewhere in that realm. First time I was ever aware of it, interestingly enough, was we could probably figure out what year this was, a winter where Great South Bay froze over and the ice began calving and people were saying, why is the bottom of the ice pink? Right. And so what the seaweed did is the ice froze to the bottom and actually started tearing the seaweed off the bottom. And we all said, or many people said, what's going on here? We now know. So that's not very in the last 5 years, and clearly not letting up. Oh, I'm seeing a lot of messages now. So let's see here. Looks like a comment. Oh, good. Mostly comments, so that's good. And well, okay, Alex.
I'm just curious. So obviously the landings in the eastern Shinnecock Bay for the hard clams have been seriously increased. Have you done any surveys about the larval clams?
Yes.
Because I think a lot of babies are very skeptical about the situation.
Yeah.
Right.
I think I have an answer. Let me actually just jump in.
I said, obviously there's been a lot of seeding in the western end of the bay.
Yes.
But it's kind of a serious distance.
It is, but in 2 weeks, so here,
Bay where
yeah,
things
so-
are productive.
so the question, just for everybody online, the question is about the clams being planted in the west, and yet the landings are in the east. So we've done a hydrodynamic model based on tides. So let me give you the facts, which are pretty exciting. When the clams in the eastern bay spawn, the larvae stay in the bay for 2 days and then go right out to the ocean and never come back. So there's no way for the eastern bay clams to repopulate themselves. The larvae are flushed out within 48 hours. And there's no way around it because larvae live for 2 weeks.
Yeah.
Right?
Yeah.
The larvae, the same models in Weesuck Creek, you get larvae go to the west, but you also get some that go to the east and that settle in eastern Shinnecock Bay. And for Tiana Bay, it's even better. They go almost entirely to the east. Some actually go out to the ocean, but you get a lot of settlement in the east because it takes 2 weeks. And so that's based on both the models and then also in the last 2 years, 3 years, we've developed a technique for actually measuring the larvae in the water column. And so what we've seen is that the clams in the west spawn. We're detecting the larvae in the spawner sanctuaries, and we're actually following them flowing from Tiana Bay to the bridge and then to eastern Shinnecock, and then you can't see them any further. And so it's a pretty exciting finding. And again, I'll credit Mike Dole for really helping to bring a lot of this together. And with we have a paper that's being peer reviewed right now by an international journal, and we believe we're optimistic that's going to be published this year. And I think, again, the science is incredibly strong. And I think it will only be accepted for publication if the science is strong. And I think that's really going to then speak to, what's going on. But again, those clams can't replace themselves in eastern Shinnecock Bay.
I mean, obviously, the eastern end of Shinnecock Bay landings have been huge.
Yes.
Anything out of SS-13 has been fantastic.
Yes.
It's been a big deal for like a lot of baymen, and I think a lot of people were wondering where those larvae came from. I know they say suspended in the word. I think some people are skeptical, like
again,
all the restoration efforts in the east end, west end of the bay,
yeah,
could possibly influence something.
Well, both the hydrodynamic models and even the most importantly, the measuring of the larvae in the water show that that's exactly what's happening.
Yeah. So,
yes, and we're thrilled.
the results, obviously,
Yeah.
Show for themselves.
Yes. Okay, so I go to a question here from Paul Stacy, and his question specifically, let's see, hydrogen sulfide, and the question about connection to mortality with hydrogen sulfide. Could the mortality be from the hydrogen sulfide in combination with toxins and low DO? I think we've looked a little bit into hydrogen sulfide, and I think the answer is that there are a few lines of evidence to make us think that that's probably not the primary mode. We know, for example, Ulva produces a lot of hydrogen sulfide. Daisy Siphona produces a lot less by comparison. So we can't cross it off the list. I think I'm pretty sure we've measured it, and I think it's not nearly as high as some of the other seaweeds. Okay. Let's see here. A lot of questions. Anybody else in the room? I just had this vision of Chris Clapp from the.
So question on the selection of stocks, brood stocks that were used to rebuild, particularly the scallop population, and other species that we've tried to restore over the years, the grass, other things, and the recognition of the impact of the warming waters. How much of an impact do you think that the selection of broodstock from areas north to rebuild our stocks had on the current collapse of the bay scallop, and what might that have looked like if we chose something from Virginia to rebuild our stock instead?
Yeah, that's a great question. And just repeating the question is, when it comes to restoration, where does your brood stock come from? And should you be getting stocks from places north and bringing them south to Long Island? And what's the benefit of that versus getting something further south and bringing it to the north? Historically, it's been prohibited to bring things from the south because of disease concerns. But I think as you're alluding to, Chris, as you move to the north, you're looking at environments that are actually in our past almost. And so organisms that are not well adapted to higher temperatures. And so, yeah, as Stephen Thomas said, he can talk more about specifically the bay scallop, for example, but we may well be close to the southern, or maybe at, Steve, you can nod your head if you think, are we at the southern extent of the Irradians?
In terms of commercial base scallop populations, yeah.
Okay, yeah. So whereas if that's the species goes down to the Gulf of Mexico, so if we had something further south, perhaps it would be doing better right now. Okay. Anyway, I had this, by the way, I had this vision where I would just be here all night, like scrolling through message after message. But I do think at some point, if students wanted to go to their posters, I'll do a few more questions here, but I don't want to have everybody in the room tied to here. But Paul says he had a second question. How many other systems would need to be upgraded to meet a nitrogen reduction target that would be protective? Are we making good progress? Well, I think Suffolk County is on the case. And so they've already identified 200,000 systems they want to upgrade by the year 2050. And they know which ones they want to do, and they've got funding to do that. Okay, here we go. So here's with regards to growing kelp. I'm just focused on the question. Do you suggest that we start growing more kelp at the same site as shellfish? Yes, I do. Keep going. Okay, let's see.
Can't grow it in the summer. It's a time question.
Yes, that's right. Oh, maybe it was, so maybe that was maybe I was missing the point there, but yeah, opposite growing season. That's right. So, and then again, that's why we've actually pivoted. We have a project supported by a New York Sea grant now to look at advancing Gracilaria as a seaweed for aquaculture, recognizing that it's actually, that's the other thing. Not only does kelp have a shortened growing season or shortening growing season with time, all those water quality impairments like acidification and harmful algal blooms are the most intense in summer. That's when we need the seaweeds to come to the rescue. Kelp's not going to do that. So that's why we're exploring things like Gracilaria and other seaweeds as well. Okay, well, in happy news, oh, they keep coming up here. Where can you locate some of the findings so we can use it in advocating? Well, I will just say, if you go to the Gobler Lab webpage and you find our publications, I pay money every year, a good amount, to make all my publications free for anyone to access. So we put out about 20 papers a year. You can, have fun reading all 20 papers each year. But anyway, you're welcome. That's one way you can find out what we're doing. And we try to also keep things going on social media. So it would be another way as well. Final question from Bob Moser. Can cultivating harvesting macrophytes in freshwater ponds help reduce HABs in those ponds, possibly as a bioextraction approach? And then recording of this, yes, this presentation will go up on the SOMAS webpage, and the Gobler Lab also has a YouTube channel. We'll be putting it up there as well. So with that, we've reached the end of the evening. So I thank you all kindly for your attention, and you can go visit the posters once again with follow-up questions. So thank you all.